Welcome to the presentation on hypothesis testing. First of all, let's understand what is a hypothesis. Basically, a hypothesis is a statement about the value of a population parameter developed for the purpose of testing a theory or belief. Hypothesis testing procedures are based on sample statistics and probability theory. So through hypothesis testing, we determine whether a hypothesis is a reasonable statement and should not be rejected, or if it is unreasonable and hence should be rejected. So let's understand this with an example, and if you followed the last lecture, we will continue with the same sort of an example where you have a population which consists of 1 million stock returns, and you have a hypothesis about the mean return. And let us say that your hypothesis is that the mean return is not equal to 0. To test this hypothesis, what you can do is draw a sample. So in this sample you might draw 100 returns, and then you check the mean of this return in order to test whether your hypothesis is correct or not. The first part of hypothesis testing is to state the hypothesis. So continuing with the example I just mentioned, if your hypothesis is that the mean is not 0, then the way you set it up is as follows. You set a null hypothesis where you basically set it up so that what you want to reject is part of your null hypothesis. So you set up H naught mu, the population mean, is equal to 0, and you are hoping that you can reject this. And then the alternate hypothesis becomes mu not equal to 0. And just to emphasize, null hypothesis is the hypothesis that the researcher wants to reject and always includes some form of the equal to sign. Alternate hypothesis is accepted when the null hypothesis is rejected. It is usually the alternate hypothesis which we are trying to assess. So what do I mean by this equal to sign? Notice that what we are after is we want to show that, or we believe that the mean return is not 0, and hence that's the way we set up the alternate hypothesis. The null hypothesis then is set as mu is equal to 0, and we are hoping that we can reject this. Also, the equal to sign needs to be part of the null hypothesis. What if you believed that the mean is greater than 0? In that case, you would have to set up the null hypothesis such that mean is less than or equal to 0. So notice that the equal to sign must be part of the null hypothesis. Once you have established the hypothesis, the next part is to come up with your test statistic. A test statistic is a quantity calculated based on a sample whose value is the basis for deciding whether or not to reject the null hypothesis. So again, that was your population. From the population you pulled out a sample with say n equal to 100, and in this sample, let's say you came up with x bar equal to 1%. So x bar is the average of the sample that you drew. And let us say that you know that your sample standard deviation is equal to, your population standard deviation is 3%. So based on this information, how do you calculate your test statistic? One of the simplest test statistics is calculated when you are dealing with population mean. Later on we will deal with other sorts of parameters which have slightly different test statistics, but the one that you should be very comfortable with for the level 1 exam is the test statistic for a population mean. So that test statistic is simply equal to the sample statistic, which is the x bar value, so that's the x bar, minus the hypothesis value, often also denoted by mu naught, divided by the standard error of the sample statistic. And we talked about this in the last lecture, so that's the standard error associated with x bar. What are the values here? Actually the formula for standard error, sometimes you might be given the standard error, other times you have to calculate the standard error based on sigma over root n. This is where the standard deviation of the population is known. If the standard deviation of the population is not known, then you should use the standard deviation of the sample, which is S, and again the denominator is root n. So in our example, what is the test statistic? We calculated the sample statistic as 1%. So 1% minus mu naught. Our hypothesis value was that mu naught is equal to 0. So I'll just write this again for your reference. We had set up our hypothesis such that the null hypothesis is that mu naught is equal to 0. This 0 corresponds to the mu naught over here, versus the alternate hypothesis that mu is not equal to 0. So the hypothesis value is 0 divided by the standard error, which is 3 divided by root n, root 100, which is 10. So our sample statistic is equal to 1/3, or actually sample statistic is 1 divided by 0.3, which is equal to, let's do this very quickly, 1 divided by 0.3 is equal to 3.33. So that is our test statistic. The third part is then to determine your significance level and to come up with critical values based on the significance level. Let's say that we want to do this test at a significance level of 5%, and if you recall, this means that the degree of confidence is equal to 95%. What you need to do is, given this degree of confidence of 95% and the fact that confidence level and the fact that significance is 5%, we look at a normal distribution. 5% means that we have 2.5% in each tail, and at this point I'll just let you know that given that we are dealing with a null hypothesis that said mu is equal to 0, and alternate is that mu is not equal to 0, this is a two-tail test, where if the data that you get has high positive values, you can reject the null, or if the data that you get shows x bar and hence the t stat, if that is much less than 0, then you are in this region and you can still reject the null hypothesis. So in any case, given a 5% level of significance, you have 2.5 here and 2.5 here. When you read this off your Z tables, you will notice that the critical values are 1.96 and negative 1.96. So the core point is that given your significance level of 5%, and given the fact that this test had mu is equal to 0, so this is a two-tail test, you then look at your Z table, put 2.5% here, 2.5% in the right tail, and come up with minus 1.96 and plus 1.96. These are called your critical values. Once you have your critical values, you compare the test statistic the final thing is compare test stat with critical values. Remember, our test statistic was about 3. So going from the previous slide, our test statistic was 3.33. So our test stat was 3.33. If the test statistic is greater than the critical value, then we can reject the null hypothesis. So if we are in this case, in this region, then we can reject the null hypothesis. Similarly, if we had gotten a test statistic that was less than 1.96, less than minus 1.96, or in this region, then also we could reject the null hypothesis. And if the test statistic had been somewhere between minus 1.96 and plus 1.96, then we fail to reject the null hypothesis. So putting this all together, I know this is repetitious, but it's important to understand. Step 1 was defining the null hypothesis, which in our case was H0 that mu is equal to 0 versus the alternate hypothesis that the population mean is not equal to 0. The next thing we did was calculate the test stat, which was equal to the x bar value you calculated minus mu naught over the standard error. In our case, this was equal to the 1% minus 0, this 0 coming from here, divided by sigma, which was 3 over root of n, which was the sample size. So this gave us 3.33. Then given a 5% level of significance, we came up with the critical values. So this was our normal distribution. 5% level of significance meant that we have 5% in the tails. So 2.5% in each tail. And based on this, the critical values were minus 1.96 and plus 1.96. Then the decision was based on the fact that 3.33 fell in this region where we can reject the null hypothesis. Had the test statistic been between minus 1.96 and plus 1.96, then we would not have been able to reject the null hypothesis. So let's now understand the distinction between one-tailed and two-tailed tests. What we have done so far is a two-tailed test where we allow for deviation on both sides of the hypothesized value. And whenever you have a regular equal to sign as part of your null hypothesis, then you will always be dealing with a two-tailed test. The basic way to understand this is that in a two-tailed test, basically you can reject the null if your test stat is in the right tail or in the left tail. So in other words, if we had received in our sample, if x bar is very big, then the test stat, if you look at the formula for the test stat, it is x bar minus mu naught divided by the standard error. Notice that if x bar is high, then the test stat will also be high, and we will be able to reject the null hypothesis being that mu naught is 0. Similarly, if x bar is very low, then using that same formula we can see that the test stat will also be very low, and we would then be in the left region, and there again we will be able to reject the null hypothesis. A one-tailed test, on the other hand, only allows for a deviation on one side of the hypothesized value. So here now, if you believe that the population mean is greater than 0, you will then set up a null hypothesis that says that mu is less than equal to 0. So in this case we can only reject the null hypothesis if the test statistic falls in the right tail. So notice that when mu naught, if we have a less than equal to sign in the null hypothesis, then we deal with the right tail. So in our example, let's say that we are still dealing with a 5% level of significance. If we are dealing with a 5% level of significance and a one-tailed test, then we are only talking about the area in the right tail. And let's say that with 5% in the right tail, the z value is about 1.65. So that's your critical value. If your test stat, so in our case, we came up with a test stat equal to 3.3. So with the test stat equal to 3.3, which falls over here, this then is the region where we can reject the null hypothesis, and all this region we fail to reject the null hypothesis. Just to understand this a little better, had your x bar been equal to -1%, then we would have gotten a test stat equal to -3.3 way to the left, and clearly then we would not be able to reject the null hypothesis that mu naught is equal to 0. So you can notice that with any negative value for x bar, which would then give us a negative value for the test stat, it would not be possible to reject the null. It's only that when we get sufficiently positive with x bar that we can reject the null hypothesis. What we've talked about so far is extremely relevant from the exam perspective, and obviously in an exam you would typically be given the significance level, and it will be assumed that the sample or the sample statistics are given to you. But in the real world, if you are actually conducting a hypothesis test, then what is the procedure you follow? That the steps are given on this slide. As before, the first part is stating the hypothesis. So you state your null and your alternate. You select a test statistic. In the examples that we've been talking about, if you are dealing with the mean, then your test statistic is simply equal to the mean minus the hypothesized value divided by standard error. And as you will see later on, there can be several other test statistics depending on what you are trying to do. So if you are testing the variance, then the test statistic will look very different. Nevertheless, it's important to come up with the appropriate test statistic. Then you specify the level of significance. So your level of significance might be 5% or 1% if you want to have a higher degree of confidence, but 5% is what's used most often. Then you select your decision rule. So what you would basically say here is, if the test stat is greater than the critical value, then you reject. So this would be for a one-tailed test. Depending on the test, this decision rule might be slightly different, but important point is you understand that the decision rule has to be clearly stated. Then this is where the real world part comes in. You will have to collect your sample, calculate the sample statistics, and then plug into the values you have up here. So your sample statistic will be calculated based on your data from here. So you do this calculation and then compare with the critical value and make your decision. When you do hypothesis testing, there can be two kinds of errors that you make: type 1 errors and type 2 errors. Let's understand how these errors come about. So to understand this table, this column shows the possible decisions that you can make, and this row shows what the actual reality is. So let's say that your decision is not to reject H naught. So basically what this is saying is that if these were your critical values, then your T-stat fell somewhere in here, so you did not reject your H naught. However, it turns out that the null hypothesis was so you do not reject the null hypothesis, and the null hypothesis is in fact true. So clearly this is the correct decision. On the other hand, if H naught is true but you rejected the null hypothesis because your critical value fell outside because your test statistic fell outside the critical value, so you rejected H naught, but H naught was actually true. So clearly this is an error, and this is called a type 1 error. So again, type 1 error is where you reject H naught, reject the null, even though the null is true. So this is a error. What about a situation where H naught is false? Actually, one important point over here, that the significance level alpha is the probability of the type 1 error. So probability of type 1 error is given by the significance level, which is this shaded area for a two-tailed test, and for a one-tailed test it would only be the area in one tail. Now come to the situation where H naught is false. If your null hypothesis in reality is false, but you do not reject the null hypothesis, this is called a type 2 error. On the other hand, if H naught is false, so your null hypothesis is false, and you reject the null hypothesis, that is a correct decision. And an important definition, the power of a test is 1 minus the probability of a type 2 error. Clearly you want the probability of a type 2 error to be low, which means that you want the power of a test, which is 1 minus the probability of a type 2 error. You want this number to be high. So the more power the test has, the better. And as a general point, when more than one test statistic is available to conduct a hypothesis test, select the most powerful. Let's now look at the relationship between confidence interval from our last reading and hypothesis tests. So if you recall, with our confidence interval, what did we do? Our confidence interval was a point estimate plus or minus a reliability factor, which was given by Z alpha over 2, multiplied by the standard error, which was sigma over root n. So the higher our confidence is, if we used a very high confidence level, which meant a low significance, then this number would be high and we would have a high confidence interval. And if we have a high standard error, then again that would cause our confidence interval to become higher or wider. So notice the role played by both the significance level as well as the standard error. What about with hypothesis tests? With hypothesis tests, again, what happens is that the significance level is important because it determines the critical value. So higher as a quick, you've seen this enough times, but nevertheless, if our significance level, the smaller the significance level becomes, higher the confidence. So low significance means high confidence, and low significance also means high critical value. So in terms of the standard error, that plays a role when we deal with confidence intervals, and the standard error obviously becomes important with hypothesis tests, because the test stat is calculated based on the standard error. So this standard error being the sigma over root n. So higher the standard error, lower the test statistic, and harder it becomes to reject the null hypothesis. So when do we use z-tests and t-tests? They are used when we are testing hypothesis concerning the population mean, and this is what we've done all along. If the population variance is known, then we use the z-table. So we calculate the z-statistic as the population mean, the sample mean minus the hypothesized value divided by the standard error. If the population variance is not known, then you use the t-table. So there you come up with a t value, which is again equal to x bar minus mu naught, and now the standard error becomes the sample standard deviation over root n. As you saw in the previous lecture, when you use a t-table, it's important to use degrees of freedom. You need the degrees of freedom to read the t-table, and this degrees of freedom is equal to your sample size minus 1. So sometimes you will actually see tn minus 1 to represent the degrees of freedom.